Okay, I guess it's about time to start. How was lunch? Good? Everybody's ready to nap? Right. Let's see where we can take this. So let's make our data fabulous and see what that actually means, because there's a bit more in the title than you might see at first. So I work for Elastic, the company behind Elasticsearch, and you might have seen our product, or you might have used Kibana and some other stuff. We'll use some examples from our world, but it's a bit more generic, actually. So that's what Stack looks like, but we can skip that when we only have 35 minutes. So knowing that I work for Elastic, and if I ask that question, what is the perfect data store, what is the right answer? No. What is the right answer? Yes, exactly, it depends. You're a consultant, right? Normally, that's what you start with, and then it costs a lot of money afterwards. Okay. I don't want to teach you how to make money, but the it depends is something we will come back to today again and again. So when I ask you a question, probably there's a good chance that it depends will be the answer, but you will see that as we go along. So it depends is not only what consultants say, and by the way, probably there is an official law, but let's call it Philipp's law now, that whenever you say it depends, you afterwards have to say on what does it depend on. Like it's not the answer to make to drag out the answer and then charge a lot of money, or just get out of the answer, but you need to define on what is the thing that it depends on. And that is kind of what we want to work on today. And it's mostly about trade-offs. Like, what are the trade-offs, especially in data stores that you want to pick or have to pick? And sometimes people promise you something like this, but in reality, there is no magic on unicorns and stuff like that. So especially around data stores, you can promise a lot, but in the end, it's mostly about picking the right trade-offs and picking the right trade-offs for your scenario. And that's where we'll go. So who knows the cap theorem? Okay, that's not everybody. We'll try to work on that. So it's based on this nice paper from the early 2000s, Brewer's conjectures. So Eric Brewer, working at Google, he gave a talk, and the idea of the talk was then turned into a full paper. And it spawned Tess Gilbert and Nancy Lynch, and they basically described that you have these three attributes: consistency, availability, and partition tolerance. You would want to have all three, but you can have two at most. So what are the three attributes? You have consistency, you have a distributed system, and it looks as if you were talking to one single system where you have a total order of commands. But you don't. But the consistency is like at one point in time, basically, you have one consistent order of commands. So if you query the entire system, for one query, they all should give you one answer, like one consistent answer that over time it can change, but at one point in time, that is the answer that the system is giving you overall. So it is looking as if you were talking to a single instance. Then you have availability. Availability is pretty much like all the instances in your distributed system need to answer. They cannot decide, I'm not sure what the cluster is up to, so I will not give you an answer. They have to give you an answer. Otherwise, they're not available. And, bless you. And the final thing is partition tolerance. You can lose arbitrary messages, especially in a distributed system. Stuff can go wrong, and all the unexpected stuff that can go wrong, you basically need to be able to sustain that and work with that. The trick is not to work as long as everything, or have a system that is working correctly as long as everything is working correctly, but as soon as bad stuff happens, then is basically when you need to make the decision, which trade-offs do you pick in that scenario? And the kind of like graphical visualization of that might be something like this. So you have these three attributes you would want to have all, but you can see there is no middle where you have all of them. You can only pick the combination of two. And it's, by the way, not guaranteed. If you design your system differently or badly, you might only have one or zero of these attributes all the times. So it's not guaranteed that you will have two of the three, because that's not a given. There are two common misconceptions. The first one is that sometimes people claim like, oh, our data center is so good, we don't have network partitions, or we don't lose messages. And that's either you have been exceptionally lucky, or maybe your monitoring is not good enough, and you didn't really see what was happening. Because there's another nice paper that actually shows that Google, Amazon, Microsoft, in their data centers, they describe how many racks and routers and full data centers they lose per year. And it's just like continuous failures are a thing, so you need to live with that. And just saying we don't have that is not really the solution. The other misconception is that consistency is in ACID, the atomic consistent isolation durable thing, and CAP theorem. And those two consistencies, or consistent, are two different things. So in ACID, it's basically going from one consistent or correct state to the next. So you have a not null constraint, for example, and you don't break that. Or you have a reference, and the reference is correct. So you go from one consistent or correct state to the next. Within a CAP theorem, it's a temporal one, basically. At one point in time, it's like consistency across the entire system. So those are two different consistencies, and that's what sometimes throws people off because they mean different things. And you can explain that to your parents or to your kids, the CAP theorem with Robinson Crusoe. So Robinson Crusoe is partitioned on his lone island. I think he was English. And basically a ship comes by, let's assume, and asks him a current question, like, who is the Queen or King of England right now? And then, since he's partitioned from the rest of the world, Robinson Crusoe has to decide, am I available or am I consistent? Because if he's answering, he's available, but he's maybe not consistent with the rest of the world. Or he can say, like, well, I'm not sure because I've been on my lone island for so long, I don't know. Then he's consistent, but he's not available because he decided not to answer. And that's really the gist of the CAP theorem. And it's a very simple paper in that it doesn't have much math or anything. It's just like this proof-based, like, okay, let's assume you have 3 nodes and you have 2 nodes here and you have 1 node here, and you write some data to these 2 nodes, and then this other node, it knows that it cannot see the other 2 nodes, and then it also has to decide, like, am I giving an answer? Then I might be out of date and not consistent with the rest of the world. Or I'm not answering, then I'm not available. And that's the entire proof, basically, and that's the general idea of the paper. By the way, does anybody recognize the island? It might be a bit hard to see right now. It was in a movie in the last couple of years. So it's this island. And we'll mostly do examples with Star Wars, so we'll come back to that. By the way, you can break the CAP theorem with def null, but that doesn't give you a helpful system, because it just always throws away your data. So yes, it's always available and also always consistent, but that's still not the system you want. So that's, yeah. There is no easy way around the CAP theorem for useful systems normally. Okay, that was the CAP theorem, and then there is this fab theory. This is a theory, doesn't have a fancy paper, at least not yet, that one of my colleagues has developed. So this is Mark, showing him at his favorite hobby, and he has developed this fab theory. And the general idea is the same. You have 3 attributes that you want to have, and you can only pick 2. So what are the 3 attributes here? Fast, accurate, and big. Fast is basically something that you answer in more or less real time. Or let's say that a human waits for the answer. So when you query the system, you're not going for a coffee, you're not going home for the day, you're waiting for the answer. So normally that's maybe up to a couple of seconds. But everything else, people will just go do something else. So we want to have something where humans are willing to wait for the answer. Oftentimes, like, I don't know, Hadoop systems might not be fast in that regard because it might take them an hour or a night or whatever to crunch some data. So that's kind of like when a system is not fast. Then you have accurate. Accurate basically means you have the exact answer that you're getting. So you get a correct answer. That one is slightly weird, like what would I do with an incorrect answer? But we'll see afterwards some trade-offs, what kind of trade-offs are around accuracy. And then we have big, and big is, I'll just say, like anything that doesn't run on my laptop. Yes, I'll run my demo on my laptop, but it is distributable between different nodes. So let's say big is anything that needs more than one instance and you need to distribute them over multiple systems. People always like this term, and I'm not a big fan, because by now this is mostly a buzzword that people are using and abusing. So let's just skip the big data thing and all the V's for velocity, variety, whatever. Let's just say something that needs to distribution over multiple nodes. That's the idea. So I guess fast is kind of clear. You wait for the answer. Big, you need to distribute it. Also clear. What is accurate? And accurate is kind of the trade-off I want to show a bit with the examples. And well, I run those against Elasticsearch, but other systems have very similar things. So except some syntax things or like the query language, everything else will look pretty familiar to other systems as well. The only thing you need to know about Elasticsearch, by the way, is the unit of scale is a shard. And basically you have an index or it's more or less a table in the relational world. So you have a thing that stores related data, and you can break that up into one or more so-called shards or pieces. And one of these shards can then reside on one node. So you break up something into 5 shards, and you could put that onto 5 different nodes. So each node is getting one specific shard. By the way, does anybody know where the term shard is coming from? Yeah, but so this is more of the trivia question. So does anybody remember this one? Maybe some people are old enough. Yeah, I think this is Ultima Online. So probably there are multiple stories to that where the term shard is coming from, but this was already written in 2009, and the story itself is older. So there was this wizard and the world in the crystal, and then the crystal was broken up into multiple shards, and each shard held a fraction of the world. And according to some people, and I like this story, this is where the term shard is coming from, and that's why lots of systems, like MySQL and others, they always call that if you break up one big index or table or whatever into multiple pieces, that's where the term shard is coming from, which is not relevant for the fab theory, but it's just a trivia thing on the side. So let's do a terms aggregation. What was the terms aggregation doing? Basically a top n, so I want the top most common term. And I'll use Star Wars terms, and Star Wars numbering got very complicated. I think by now this is number 4, but this was the very first movie that came out. So from this movie, somebody counted how many times do specific terms appear in that movie. And you can see Luke appeared 64 times, R2 31, Alderaan 20, etc. So these are the terms. And basically, I store 64 documents with Luke, and then 31 with R2, etc. And at the end, I want to run a query and ask, like, which term is the most common one and how many times does it appear? Sounds simple enough. So I create an index with 5 shards, and then I insert documents. By the way, the first, or the odd line is always the metadata, so I put that into an index called Star Wars, and then the even line, the second one, that is the actual document. So I have a document with 1 attribute word, and 1 value Luke. So I have 64 Luke documents, and then 31 R2, etc. And I store those documents. Okay, you could visualize that, then it might look something like this. And this is exactly what the terms aggregation is doing. Like you have this tag cloud, and you want to figure out which are your top terms, and then according to their size, that's how many times they appear. Is it relevant if you're slightly off here in the terms aggregation, like if it's 62 or 64 Lukes? Not really, but you probably want to have that aggregation in a more or less cheap fashion and pretty quickly. And that's exactly the trade-off for what the terms aggregation is often used for. You want to get a quick idea, what are the most common terms and approximately how many times do they appear. So this is the use here. But let's look at the actual query and what we are doing here. So I have this running here. So I've already, like in every good cooking show, I have prepared the data, so the documents are inserted. We can simply search and check if my documents are here, so you can see I have 64 Lukes. So here I'm searching explicitly just for Luke, and it tells me, okay, I found 64 Lukes, we're good. Now we can run the actual terms aggregation. So here you can see this is an aggregation on terms, on that specific field, the word, and size 1 basically means I want to have the top 1 term, so I only want Luke, basically, and not the second and third term. One thing that's sometimes confusing is that size down here basically means I want 0 of the actual documents, because I'm not interested in the actual Luke documents. So I'll get back 0 of those. You could also get some actual documents of that back, but we don't here. If I run that, what is the answer? Yeah, if I run that, and then you see, it's only 60. And that might not be the answer that you were expecting. And I know that some of you will say this. So, why are we counting wrong? Like, this seems like a very simple use case. Why are we already counting the simple use case wrong? So, I have cheated a bit. So, what I've done is I've prepared the data in a specific way that specific shards have way more Lukes than others. And by skewing the data that way, we are counting wrong. So first off, what have I done? Like the first 10 documents, so the first 10 Lukes go to that routing key, and the routing key basically determines to which shard a document goes. And so from 0 to 9, they are more or less evenly distributed because I just pick incrementing routing keys, but the 54 remaining looks all go to the same routing key, 0. So I have one shard, this shard here, that will have most of the looks. And then the other ones might be forgotten in the query, and we'll get to that in a moment. But how the routing information is used basically is you take that routing key, you hash it, and you count it modulo the number of primary shards, so modulo 5 in our example, and that will determine onto which shard you go. Why do I hash the routing key? Why don't I take it immediately? For even distribution. So if you pick the routing key yourself, and it could also be a string, like a name, and then you might have more names starting with E, because that's the most common letter in English, for example. And the hashing basically guarantees that amongst your entire key space, you have even distribution of values. And then you basically, with modulo, you slice them into 5 even chunks, and then your data should be evenly distributed, unless you kind of manipulate the routing key like me. Then you will have skewed data. And then you can already see this is what you will get out of the shards, and you could, for example, see that this shard here has 71 documents, and this only has 26 documents, because I faked the data a bit and moved it around in a way that it's not evenly distributed and it actually fails for our specific use case a bit. And how do we calculate the top n results? What we do is, size was how many results do we want to get back? What was size in our query? 1, because we only wanted one result. We multiply that by 1.5 and add 10. So we have 1 times 1.5 plus 10. How many results are we getting from each single shard back? 11, 12. It's 11, it's rounded down. So basically what we do is, because if you have a lot of terms, you might have 1 million unique terms. And it would be kind of wasteful that you want to have the top most common term, and then every single shard is calculating you a list of the 1 million terms and sending over the list of 1 million terms, because that's a lot of network traffic, but there's also a lot of stuff to calculate in heap. And it might blow up your heap, so you don't want to do that. That's why we assume if your data is evenly distributed and you want the top 1 term, we just calculate the top 11 and combine those, even if you have 1 million other values in your shard. We will only take the top 11 to centralize those. And because I have prepared the data the right way, the one shard with most of the looks, well, that has a lot of looks, but we are missing some shards which only have 1 or 2 looks, and that's why we're counting wrong. And that's exactly what is happening here. So we have 11 results per shard, and then we have 5 shards, so we aggregate 55 sub-results basically together to get the top 1 term. That's how we calculate those. You can, by the way, add some parameters to that query. I have done that here. Let me scroll that over. So here I saw show term doc count error true. If you run that, it will show you I have 60 looks, and that is basically the lower bound. But I know there could be 4 more looks. How do we know that there could be 4 more looks? Because basically we know if Luke is in the top 11 results, we're not contributing anything to the error of that shard. But, no worries, if we have a shard that doesn't contain Luke in the top 11, and we know the 11th position has like 2 or 3 hits, then we know there could be another document with 2 or 3 Lukes that we're missing basically in the top 11. And that's how we basically know where the error bound is coming from. And we know, well, 60 is the minimum, but it could be up to 4 more. And then, when you change the precision threshold to, here I set the shard size, which used to be 11. I set that to 20 explicitly. How many unique terms do I have in my document set? 16, so this needs to be correct now. So when I run this now you see, okay, we have 64 looks, and we know we got all the documents from all the shards basically, so there cannot be any error in here. But it's a bit more expensive, because now we get 5 times 20, or actually only 16, because I only have 16 unique terms. But we have more aggregate, or more results to calculate and then aggregate together. So this is just a trade-off, like how much accuracy do you want, and what is the trade-off in then the big and the fast, basically, that you can do here. Okay, that was one here. Let's go to another aggregation, the cardinality aggregation. What was the cardinality aggregation doing? How many unique terms we have in our data set? So the naive implementation basically would be something like this. You have, you create a hash set. So if you take a value and hash it, it will always get to the same hash value, and then you basically just have the unique values basically in the no duplicates hash set, and at the end you do a size. So the first loop would be overwritten by this loop, so you only have unique elements, and basically you then do a size on unique elements, and that's how many unique terms you have. How will this scale? Pretty linearly. Like linearly with the number of hash operations you have to do, but also linearly with the amount of memory you will need. Because every unique document, or every unique term here, will add something to the hash set. So it will just keep growing and growing. And if you have 1 million unique documents, it will be quite a lot of stuff to store. So we don't want to do that. So we could actually do that differently. This is very related, but at first it doesn't look like it. In a coin flip, what is the calculation if you want to flip like 3 heads in a row? What is the chance of that? Yes, 1 divided by 2 to the power of 3, because 2 is the number of options, and then you have three throws in a, or 3 heads in a row. And you see if you have like 5 heads in a row, it would be to the power of 5, etc., so it would keep growing a lot. So it's generally 1 divided by 2 to the power of k. If you have more heads in a row, it's more unlikely, and you probably need to have more throws. And you can take that general concept and actually, it's then called probabilistic counting, and bring that to the unique values that you have in your data set. Because what you do is you hash your value, and then you have a binary representation, and rather than counting heads or tails, you're counting leading, and leading is from the back in that example, leading zeros. So for example, if you have 3 leading zeros, that's pretty much the same chance as if you had the 3 leading heads. And basically, 3 leading zeros is the chance of 1 out of 8, basically, because this is like 8 possible values. And this is how you can calculate it. So what you basically do is, rather than hashing everything and remembering all the values, you hash everything, but you only remember the highest number of leading zeros. And based on that, you have an approximation of how many unique values you have in your data set. So basically, you hash all the values, you always remember how many leading zeros you have, and based on that formula, that's what you will get. However, sometimes you're just unlucky and you have like 1 too many or 1 too much, and it always jumps by a power of 2, so the number of unique terms could be a bit jumpy. So what you want to have is you want to even that out. And what you can do is, and that general approach is called LogLog, it's called probabilistic averaging. And what averaging here basically does is this greenish curve here, which is wider. This is like if you're using a single hash function. And then here, this is the actual true cardinality. If you're using multiple hashes and would combine them together, then you would have a curve like that is narrower and closer to the actual cardinality. So the general idea is you could hash that multiple times and then average out over those multiple hash functions. Will that be very performant? Not really. So what LogLog basically does is, and there's another paper based on that. What that does is it uses a single hash function, but since you assumedly have enough values, it will bucket them into multiple groups. So you will basically hash look. These are not the actual values for that. This is a bit made up. But you will use these 4 bits here for the bucket. And you will say, look, this is the bucket here in binary representation. So this is the bucket 4. And we have 3 leading zeros. And then we have the bucket 9 for R2, and that has 4 leading zeros. So you use a single hash function, but you get basically multiple estimators out of that. And then you can average out over all the different buckets you have. What is the highest number of leading zeros you have seen per bucket? If you average that out, you will get an approximate number of how many unique values you have in your data set. And you only need, for every single bucket, you only need to remember 1 number of how many leading zeros you have. So it's much easier to keep in memory, because it will need much less memory. Of course, it's not exact, but it's an approximation. Then that's the logarithm, or the algorithm from that paper, which is probably too much for today, so we'll glance over that. And then Google wrote a paper about HyperLogLog, where they basically took the LogLog algorithm and improved it to have a better error rate. And the general idea of HyperLogLog which is now slightly improved again, and now it's called HyperLogLog++, that the error rate should only be 1% or so. So it's very fast, and it's pretty accurate, and it will look something like this. So to run the actual query, so yeah, timing-wise, we're still okay. So what we do here is I run a cardinality aggregation on the word keyword. How many unique terms did we have? 16. I set the precision threshold to 10. This is basically how much memory will we use, and up to that value, the count will be exact. For higher values, it will be an approximation. If I run this, we get 17 out of that, so it's close but slightly off. And you can basically tune that with the precision threshold. I mean, my values are very small, so normally you wouldn't have problems with those. The default precision threshold is 3,000, by the way. You can set it up to 40,000. If you set any higher value, it will be capped to that. And the nice thing about that is that it will translate directly into memory use. So you multiply the precision threshold by 8 bytes, and that is how much memory your calculation will need. So it's very easy or stable to calculate how expensive will my cardinality aggregation be. Whereas if you have no idea how many unique values you have and you run a cardinality aggregation, it might just blow up your heap because you have no idea what you will get out of that. We've tried to draw that out in the documentation, that if you use a threshold of 100, 1,000, and 10,000, how high the error rate based on the actual cardinality will be. And you can see with 10,000, it's like here it's 1.5% or so, but normally it's much lower. So you can basically pick like how much memory will I use and how exact should my results be, approximately. And then if I turn it up to 12 already, then it will already be exact or hit the right value in my example. So, because 35 minutes is, oh no, let's do this. This is a good one. Should you pre-compute hashes? So you could pre-compute the hashes on the client side and store them in your documents. Should you do that? It depends, obviously. But on what does it depend? So if you have a large data set or a high cardinality, then it probably pays off. If you have a low cardinality or a numeric field, because numeric fields are very performant to hash in modern CPUs, then it probably won't pay off to pre-compute the hashes. So these are the trade-offs for this one here. We tried an improvement. There was another paper, and it described something called log beta. We had a pull request for that, but it didn't improve anything for us, so we never merged the pull request. There is another paper called HyperLogLog sketches, which is said to improve everything, or improve the error rate a bit. We haven't implemented that yet, so we're not sure if that will actually improve something or not. Maybe we'll get to that at some point in the future. We'll skip the searching part. So there's another trade-off around searching that we can skip. Something. Let me just include this one. This is my favorite comment whenever somebody asks, like, how fast is this really? Or how does this compare to any other system? This is pretty much what you're getting. So anytime a vendor does a benchmark with themselves and one of their competitors, this is what you should expect from them. So they find similar conditions, and then in one condition their system is performing very well, and in the other one they basically killed the other system. And I remember a couple of years ago, I think, Couchbase, DataStax, and MongoDB each did a performance comparison with their two competitors, and each one managed to find some scenario where they were at least twice as fast as the others. So this is normally what you get out of those. So we can skip that one. Something you might want to use a single shard, which is the default in Elasticsearch 7, because every shard has some cost, and many people had too many shards. Simon, one of our tech leads, he said, use a single shard until it blows up and figure out how many you will need in the long run. What does that mean? So we can actually take our data, and let me quickly do that. We can take our data, and basically I shrink my 5-shard index down to a 1-shard index. This is what I've done here. If I search for the most common term, and I run this one here, will this be now correct, yes or no? Yeah, no, this one doesn't depend. So you remember in the terms aggregation, when we wanted the top 1 term, we were taking the top 11. If we only have a single shard, the top 1 will be in the top 11 of the 1 shard. So if I run that one here, then that works and is correct. With the cardinality aggregation, does that change anything? This one doesn't change, because this is not really aggregating much per shard, but this is just the general approach of the cardinality aggregation. That one doesn't bring anything here. Some people might say now this was a cheap move, because what did we trade here now? Yeah, so we had, in terms of the fab theory, the fast, accurate, big. We got, especially, or at least for the terms aggregation, we got the accuracy, but then the big, the scaling factor. With a single shard, we cannot scale beyond one node, so we kind of traded that here. So this is the trade-off that we picked in that example. So to wrap up, it's a bit about trade-offs and saying like it depends and then figuring out what the depends on is. We covered the cap theorem and the fab theory, and that's it pretty much for the data stores. I think we have 1 or 2 minutes left. I will unplug so the next speaker can plug in, and we can do questions in parallel, I guess. Also, I'm not sure if there are stickers left, but I left some over there, but they might be gone by now. Questions? Yes?
So about the count estimation study. So we are assuming that we have an estimation ourselves in order to get a more accurate estimation. Or if I follow your story correctly. So I have to have a rough idea of how many unique terms I will get.
Well, no. The precision threshold basically says up to this value it will be exact. For higher values it will be an approximation. And then you have an error rate of 1% or so maybe. And for most cardinalities that is a trade-off that makes sense.
But if I want to make this accuracy is very important, then I have to know the precision threshold.
Yes, but you can only set the precision threshold to 40,000 if you have more unique values. By default, there is no way to do that. The only way how you could do that is basically you could do a filter and then get a subset of the data, and then basically aggregate multiple subsets together afterwards. But that's a more manual approach. There is no other way to do that by default, because it might just be too memory intensive.
Okay, let's give a hand.
Thanks a lot.
Thank you.
By the way, normally I try to take a picture with you so I can prove to my colleagues that I've been working. Because we're a fully distributed company and nobody knows where I am today. Can you all wave? Wave, wave, wave. Thank you.